Hello and welcome everybody to the course Crystal Engineering Chemistry Beyond the Molecule. In this video, on the second, so in the next two videos, we will speak about polymorphism. And how shall I say, during the preparation of this slide, polymorphism, once again, I was really impressed and fascinated about this phenomenon. Well, have a look. Polymorphism. What is polymorphism? So, it is the phenomenon in which the same chemical substance, the same molecule, exhibits different molecular arrangement in solid state. So you have one molecule, and then have a look on the crystal packing, the molecular arrangement, and you will see where could be different properties in which way the molecule aggregate in solid state. This is polymorphism. And why is this interesting? Well, this different molecular arrangement could lead to different physical and chemical properties. So that means that the properties, several properties, I think I said it, several properties of a substance are not directly attributed to the molecular structure, but they are attributed to the molecular packing. You see it here, morphology, solubility, yes, the color or melting, sublimation temperature, density. Think about what I said about water and heavy water. Nice example talking about density. And physical properties important for application, thermal or electrical conductivity, and so on and so on. These are only some properties which are related to a molecular arrangement, not to a molecular structure. And you see, this is important. It makes sense to think about polymorphism. One example, nice example, talking about Roy. This is the molecular structure of Roy, a typical organic compound. And depending on this theta, this angle here, yes, there's a possibility of rotation of this bond, only depending on this angle, you will get several properties. And last year or 2 years ago, we discovered a new one, or they obtained another polymorph. So in this case we have 10 polymorphs. I think in this moment currently we have 11 polymorphs. And around about 7 polymorphs, the molecular structure, the crystal structure was determined. Only with theta angle. Roy, this is the name, the UPAC name of Roy. Roy means because there's so many polymorphs and you see different colors. We said red, L, O is orange, for example here or here, ON, orange, and yellow, L, epsilon, O, yellow. And have a look, the melting point, the differences. Here, for example, we have a melting point here from 97, for example. 97. On the other side, you see we have a melting point here from 115 roundabout. This is difference around about 18 degree. Okay? Melting point difference. Of a color, we talk about the color, all with different colors. And the angle. The angle is here in the range from around about 20 degree and up to 112 degrees. Nice example how, well, the molecular arrangement can have an impact on the properties. Why? We will talk about several times later about why. There was a very nice sentence from Walter McCrone in the 70s who said, well, it's not so spacey polymorphism. No? He said every compound has different polymorphic forms. And it's only the question how intensively you investigate the molecular arrangement of substances in solid state, and proportional to the time and the energy, and I would say the money you will able to put in, you will find polymorphic forms of one compound. And well, I would say this sentence is really true. I would not say all compounds, but a lot of compounds, yes, have polymorphic behavior, and you have really time when you're working very carefully and think about experiments and crystallization pathways and so on. It could be possible to find new polymorphs of a lot of compounds. On the other side, if you look in the crystal structure data, the Cambridge crystal structure database, when you will see that around about only 5% of organic structure show polymorphic behavior. Yeah, not more, 5%. Okay. Polymorphism. Well, polymorphism is not a topic from this year or the last years. No? Polymorphism is known since a long time. And I would say one of the earliest developments of polymorphism is going back in the 19th century. Mitscherlich. Mitscherlich was the first, so I know, and several other guys know, who published polymorphism, this phenomenon, and he obtained different polymorph of arsenate, arsenate and phosphates, no? Both arsenate and phosphates. No? If you switch from arsenic to phosphorus, you get the same compounds. Very often, by the way, very often if you switch from phosphorus to arsenic element or compounds, very often you will find the same polymorphic behavior and general structures. It's crystal structure very often. This was in the 19th century, the beginning of the 19th century. A little bit later, Wöhler and Liebig investigated benzamide, 1832, where it was discovered two polymorphs of benzamide. And very crazy, this was 1832. And some years again, 2007, Angewandte Chemie, top-ranking journal, the group of Dinnebier and Breu published the third polymorph of benzamide. It was important enough, this polymorph, that this contribution was accepted by Angewandte Chemie to 2007. As you see it here, for 175 years, Friedrich Wöhler and Justus von Liebig developed and investigated the polymorphisms of general crystals, and until today is one task to control the crystallization behavior to get special polymorph. Something like this here in the abstract. No? And here are the different polymorphs of benzamide, A and B. These are the polymorphs suggested and generally investigated by Wöhler and Liebig. Well, in this time they were not able to think about and to determine the crystal structure, but they found crystals of these two forms. Okay? And here the third one for the group DNB and Broy. Well, what is polymorphism and polymorphs? Which type of types of polymorphs do you know or exist? Well, it makes sense to classify, to think about the different forms of polymorphs. Well, starting with conformational polymorphs. I would say this is the most easiest, very easy to accept polymorph. For example, you have this compound here, venlafaxine. And if you look to the crystal structure, or generally if you look to the outcome, what we obtain from the crystals and analyze, then you will see you have two polymorphs. You will be able to get two polymorphs, and the difference is attributed to conformation. This is an overlay of two polymorphs, or venlafaxine. The green one is one polymorph, and the red one is the second polymorph. And you see very nicely with the differences here in the conformation here for central asymmetric, the chiral atom here. You see very nicely. Typical example for conformational polymorphs. Okay, next type. Talking about tautomeric forms. Well, this is a very well-known examples for tautomers. Omeprazole, and here's the difference. Look here to the methoxy group substituents here, and I would say 1, 2, 3 position. On the other side, 1, 2, 3, 4 position. 3, 4 position here. These are tautomers. But if you're looking at crystals, yes, so molecular arrangement, talking about solid state, is very important to confirm that tautomers are no polymorphs, because tautomers, both compounds, are different molecules. This is one molecule, this is the second molecule. And there's no equilibration in solid state. This is the great difference, the big difference in solution. So in solid state, in around about 98%, you will find a thermodynamic stable compound. No, you will not find, in general, mostly you will not find both forms, and you will not see any equilibration in solid state. Once again, tautomers are no polymorphs. On the other side, tautomers, going back, thinking about this with both forms and think about the viewpoint of crystal engineering, you will design desired compounds of these compounds. Well, this is a really interesting task, working with tautomers. Well, there are some very nice examples in the literature. You see, 4 years ago, once again, Angewandte Chemie, this is the group of Marshall and Hudson, were able to obtain the enol form of barbituric acid. This is well known. The ketoenol tautomer behavior of barbituric acid is known since, I don't know, long time. If you look in the solution, you will find this is the keto function, this is a keto form, and this is hydroxy form. Difference here. There's only here ketoenol tautomers. Typical examples. Well known that this phenomenon exists in solution. And now we found the enol form. Question is how? This is typical for crystal engineering, thinking about crystals. By tuning the crystallization conditions. And this is copy-paste from the abstract. The thermodynamically stable thermodynamically stable enol crystals form of boracic acid previously prepared as powder first by grinding or slurry methods. Grinding and slurry methods. You can think about if you ever heard it, what it is. Some of you, I know, some person who are listening this video have heard it, but not all. Has been obtained as single crystals by slow cooling from a methanol solution. The selection of an enol crystal was facilitated by a density gradient method. Grinding, slurry, and then a density gradient method. And then you can get the enol form. And the question is, what do you think? What is the difference in the crystal packing? We have a keto function here. So in this case we have 3 keto function here. CO double bond 3 times. And 2 amino function here. So you can say with an amide group, and an amide group. And in this case, the number of amide groups is reduced by regarding this enol form. Has this an influence, and in which way has this an influence of a crystal packing? Think about your own. You can maybe, I would say, my suggestion myself, stop this video in this moment. Yes. Think about by yourself. Take a sheet and draw your suggestion. Okay? Well, when you can stop now. Okay? Did you try? And now have a look. Have a look on the crystal packing. In this case, this keto form, amazing, for me amazing, as I said, we have several amide interesting synton groups here, several, one this direction or this here or this, but only one of them, yes, forms interesting or forms syntons here with intermolecular interaction. Yes. And additionally, you will find the one point intermolecular interaction or keto function with a neighboring amino group. On the other side, in contrast, if you look to the enol form, in this case, really 2 amide groups, 2-point syntons, are observable in crystal structure, and also interesting, one keto function, here the keto group, is involved in 2 different intermolecular interactions, with amide pattern and 1-point interaction to neighboring hydroxy to the enol function. So enol function here forms 1-point hydrogen bonds with a neighboring CO double bond. So, did anyone suggest successful? Next question. And to answer this question, this is necessary to have a look in this contribution. It's very easy to find, Angewandte Chemie. It's very easy to download. We have access to Angewandte Chemie, so university. Question is, first compare the crystal structure. Whole crystal structure. Try to describe the packing, the whole crystal structure. And the second point is, how can you control the conversion from A to 2 or 2 to 1? So I showed you how you can get from 2. which parameters allows you to convert 2 to 1 or 1 to 2 by crystallization. Which parameter control 1, 2 and 2, 1 conversion? Have a look in the contribution and maybe we'll talk about the examinations. Well, as I said, tautomers are in general interesting tasks. Interesting tasks in crystal engineering. And well, for example, you have a substance and the substance crystallize to different tautomers. One is thermodynamic stable and the other is kinetic stable. And now you will get, now you will try to prepare to obtain co-crystal of both tautomers, for thermodynamic and the kinetic stable tautomers. One example is here, so by Acaroy, once again, is this diazaporin. Diazaporin, you see it here. And the difference once again is here the location of a hydrogen atom here. On this side, on this side here. Okay, this is called the 3H. This is called 1H. The 1H, well known from calculations, is the metastable tautomer, and this is a thermodynamic stable tautomer. Okay, task co-crystal of different tautomers. The approach is, keep in mind what we said about hierarchy of hydrogen bonds and general intermolecular interaction. You use your knowledge and you use the results from predictions of hierarchy in intermolecular interaction. Yeah? Better donor acceptor, and you will get the desired tautomer. Thinking about what's a better donor acceptor groups pattern to use in co-crystal experiments. From prediction, this is known, as I said, this is the thermodynamic stable, and the prediction said dimers are preferred. Hydrogen bond dimers are preferred in this case here, no? Between the imidazole NH, no? And the pyridine N atom from the next here. So where's here? This was an interesting functional group for 3H. In the case of 1H, the metastable tautomer, you will say, the prediction says the result is that catamer chains are preferred. Now, this is the dimer, yeah. And in this case, you see the 1H, you will see the formation of the chains. Here, this is preferred. Okay, this is prediction with other tautomers. How can you use it? Question is, which are suitable coformer to stabilize this systems and to stabilize this systems. And the group of Acaroy, what have they done? They use halogen bond donor to stabilize the dimer here. They said, okay, this dimer by itself will be formed. You must only stabilize it. We stabilize by halogen bond donors. On the other side, we look in the crystal structure database, Cambridge crystal structure database, and they saw that urea very often stabilize such systems here, so 1H systems. Yeah, and you can use this urea for stabilization, and with forms, and this is a link, the linker. Very nice, you see it here. This is our two compounds, and something like a chain is forming here, and because it has a second group here, second interesting position, with stabilize with change by additional interaction. So we have a chain here, and this is stabilized by urea forming a second interaction. Very nice example, I would say, from my point of view, very nice example of crystal engineering, thinking about the task and an approach using hierarchy and prediction to get a very interesting result. Okay, next point, isotopomeric polymorphs. We talk about very quickly. Sometimes, only sometimes, in some cases it's possible to, only by switching from hydrogen to deuterium, it's possible to get a new polymorph, where I've shown you in the case of pyridine, this is the crystal structure snapshot of the crystal packing of pyridine, with Z prime is 4. On the other side here, if you switch now to deuterated pyridine, with the Z prime is 1, you get the other new polymorph. Okay. Next point, pseudopolymorphs. Pseudo. This is the keyword, the key phrase. And similar like tautomeric polymorph, I would say, in general, we were talking about hydrates. No? Hydrates are no polymorphs. No? Sometimes we talk about, sometimes we will find a hydrated form, but a hydrate is not a polymorph. No? We have, depending of a structure, depending of a molecule, and so on, and you will get different amount of water in the crystals, semi-hydrate, and so on and so on. No? And this is for one example, orchinol. This is the poor substance, I would say. There's no solvent inside. On the other side, if you have a look here, two hydroxy substituents attached to the backbone, and it makes sense if water is present, when you will see additional hydrogen bonds between water molecules on one hand, on the other side here the molecules, no? Forming here the hydrated form. Once again, hydrated forms are no polymorph to the non-hydrated forms. Okay? With this one, now the next, now the story becomes mystery and very interesting. That's what I said in the beginning. I'm always fascinated about polymorphs, talking about concomitant polymorphs. What is it? This is the phenomenon of simultaneously appearance of polymorphs. You have one compound, you crystallize it, and you will get two polymorphs at the same time, same moment. No? Two examples, one from the inorganic side, also in general, sorry if I got it. This is very strange for crystallization, because crystallization, you know, is a form of purification. Yes? In the practical course, you learned that if you want to purify your compound, the best way is, or one of the best way is to crystallize it. No? And concomitantly crystallization polymorphism, this is so antithesis of crystal engineering. No? You cannot control the crystallization. No? Yes, it's going out of control. Crystallization, you can say. No? This is concomitant polymorphs, out of control. And one example from the inorganic side, inorganic topics here, where if you look in the mercury iodine, and you crystallize it, this compound, this mercury compound, you directly, in the same moment, you will get different polymorphs. This is a snapshot, microscope. See different red, yellow needles, 3 different forms. On the point, from the organic chemistry point, once again Roy, if you crystallize for methanol, for example, at 50 degrees, something like this. We tried it, it really works. You will get simultaneously yellow and red polymorphs. Same compound, epsilon and the OP form of rhodium. Strange, huh? Another examples about this coumarin, substituted coumarin, this is the compound here, and you can really separate by controlled crystallization, you see it here, from an acid, an organic acid at 23 degrees, yes, I would say a little bit so ambient temperature from the organic acid, well, you will get form A. If you crystallize this compound from a solvent mixture, typical organic solvents, not acids but solvents, chloroform annexate for example, then you will get form B. Well, and only by switching the temperature, with this ambient temperature here, 23 degrees roundabout, at low temperature, you will get both forms. Very nicely, you can understand because decreasing the temperature, you increase the crystallization speed. Okay? And in this case, rapidly, both forms crystallize simultaneously, form A and form B. But this next example is very nice to show that crystallization is sometimes very strange and not so easy. You know? The aim was to crystallize, to get crystals, co-crystals of these both components. No? Yes, we see we have some comparable backbone and comparable substituents. The difference is only, in this case, is one nitrogen in the backbone, and in this case we have 2 nitrogen in the backbone. Well, what I have done, the crystallization experiment was a mixture of both compounds, solved in butanol water solvents, yes, and crystallize by slow evaporation. Well, question to you, what do you think? What was the result? Yes, once again, you take both compounds, dissolve it in a butanol water, and then slowly evaporation. Or open tube, for example. No? What happens? The result is, for me it's amazing, you will get simultaneously five crystalline materials. You will get 3 different polymorphs of 1 concomitant polymorphs, 3 of this one. You will get the pure form of form 2. You will get a hydrated form of form 2 because this is a mixture with butanol water. And you will get no co-crystal. Yeah, you see, with the theory and practice, so it's not so easy thinking about what could happen or what was the predict, suggest any results. Very nice example, but sometimes really amazing crystallization. And the question is why? In general, what is the reason that you can obtain concomitant polymorphs? What is the reason that you can obtain such different crystalline materials?